So, good morning everyone. My name is Aki Nakamura. I'm in the Resources Division in the Mineral Systems branch. And I thank the GA Pathways group for allowing me to talk about today about the exploring for minerals and petroleum resources. So, going back to what Megan was saying near the end, I'll go back to one of her slides where the oceanic crust has collided with a continental crust and has been subducted. This sort of thing pushes down material from near the surface and then melts it and produces volcanoes. And also with continental crust colliding, you produce mountain ranges. So what I want you to get out of this is that these systems are big. They're continents colliding, they're oceanic crust getting subducted hundreds of kilometres down into the earth. They are massive processes, and that's how mineralisation occurs. It's when deep things get moved around in the deep earth and get forced up towards the surface. The source of the metals that we find in mineralised deposits are from deep within the earth. So yes, they're massive events like trucks colliding, and you have a large event. So knowing that it's these plates colliding that produces mineral deposits that moves magma and metals from the deep within the earth to the surface, where would you find mineral deposits if you look at the tectonic setting? Well, you might find it in subduction zones, as Megan was pointing out, in South America, west coast of the US, Indonesia perhaps, and Himalayas, where the Indian plate is colliding with the Eurasian and producing a massive mountain range. And so if we plot an occurrence of mineralisation, in this case volcanic arc, volcanic arcs are produced from subduction zones, the red area highlighted is where you have mineralisation, or this. And the yellow circles shown where you have giant ore deposits relating to that system around the world. And what you do find is that generally, yes, they do coincide with where you have subduction zones, well, over here, subduction zones today. But you also find that you have occurrences in the middle of plates. And as Megan was pointing out, this is because the Earth didn't always look like this. The subduction zones that are there today weren't always in that location. So, we're going back to the previous GA Pathways talk. We have plate tectonics and the Earth is dynamic. So if you go back millions and millions of years, the Earth didn't look like this with the continents today. They were joined together, and it didn't look anything like it is today. Going back 340 million years, Australia was connected to Antarctica in India, and it was called Gondwana land. And here, this line here with the jagged edges, not going north-south, shows where the subduction zone used to be. And related to that, volcanic arcs, or a string of volcanoes associated with that subduction. So this is an artist's impression of what New South Wales might have looked like in the past. Energy systems also occur from very big events and large processes. So going back 105 million years, Australia was connected to Antarctica still, but starting to pull away. And Australia was moving north. This opened up a narrow and shallow sea between Australia and Antarctica, and that's where sediments were deposited. And as Megan pointed out, sedimentary basins are where you find petroleum, oil and gas resources. So energy systems also occur from plate tectonic motion. And as Australia moved north away from Antarctica, here you have sedimentary layers. Within the continental sediments, you'll find coal, because coal is produced from old plants and trees, whereas oil is produced from, or the source of oil is from marine sediments. Okay. So, much of the Earth looks like this. It's covered by water. The oceans cover about 70% of the Earth. Much of Australia looks like this. It's pretty bland, it's pretty flat, and you can't see much on the surface. It's covered by sediments. But that doesn't mean to say that there's nothing underneath. As Megan was showing, we do have mineralisation and we do have deposits in Australia. So that's because underneath there used to be subduction zones, as I was pointing out before, and magmatic arcs, volcanic arcs, and mineralisation occurring. But how do we find these when it's obscured by the cover? Well, first, let's go to cake, as we love talking about cake for some reason. Here you have a cake that is covered with icing and sprinkles. So if I were to ask you, well, what's inside it? How can you tell? Any ideas about how you might find out what's inside? Well, you could cut it, but this is an analogy about the Earth, and it's very difficult to cut the Earth. So one thing you might do is lift it, right? You're seeing how heavy it is. So seeing how dense it is, if it's light, it might indicate it's a sponge cake. If it's heavy, it might be more like a fruit cake where it's got dense material inside. So that's like a gravity survey that we do. You're seeing how heavy the thing is. If you also had access to, say, an ultrasound machine, you might do a scan and see what's inside of it. And that's using sound waves and getting reflections from what's inside. And once you do the scan, you might get a fuzzy picture that looks something like that. And that's like a seismic survey, right? You get a fuzzy thing, it's got some lines. You can see from this scan that there's something going on in the middle. It's not a standard cake, it's not just layered, there's something going on there. And so from that, you might use a toothpick or a skewer or something, have a poke around, and that's like drilling. And you'll get a good sample from that, you'll see what's happening inside. And once you do all that, you'll find that in this case we've got a piñata cake. So, what did we find out from that cake example? It's that rocks have different properties, like density, that you can measure and differentiate. So, here we have a list of different rock types, and we have increasing density towards the right. If we group these together, broadly speaking, into sediment and basement materials, you'll find that sediment in general has lower density, about 2.3 grams per cubic centimetre, and basement materials are a lot heavier, at about 2.7 grams per cubic centimetre. So by doing gravity surveys and mapping these, the distribution of these materials, you can find where sediments occur and map where the sedimentary basins are. And also similarly with magnetic properties, here we have magnetic susceptibility, which is basically how magnetic a rock is. Different materials again on the left, and then increasing magnetic susceptibility towards the right. Again, we can group these broadly into basement material and sediments, and you'll notice that the basement material has higher magnetic properties to it. And I've got an example of a banded iron formation here, which contains magnetite, which is very, very magnetic, as you can see on the diagram there. And if I stick a magnet to it, it'll completely stick to it and you can hold it upside down. So we've got some different rocks here at the front, so you can have a play around with those after the talk if you want. Okay. So what do we have in our exploration toolkit? We can conduct gravity surveys and measure the density distribution. We can do magnetic surveys. There are various electrical methods, seismic to produce images of what's happening underground. Remote sensing, you can use satellites and get the different reflectance of materials at the surface. Drilling, geochemistry, geochronology. We use all these techniques to develop an understanding of what is occurring in the ground. So let's talk a little bit about seismic surveys. You can conduct seismic surveys on ship. This is Kairei, which is a Japanese ship that we used in the Lord Howe Rise project. And basically what you're doing in a seismic survey is creating an acoustic signal from the ship, which penetrates into the subsea floor and reflects off various layers. And you detect those using hydrophones, and you can start to map out by basically echo sounding what the layers and the structures are. And you can also do the same thing on land using trucks. You'll notice that these trucks all have pads, and they lift the truck off the ground, shake the ground, and that's how you create your acoustic waves. From that, you'll produce a seismic image, which is very fuzzy and just lots of lines. And you ask, why did we spend millions and millions of dollars just getting a fuzzy picture like that? But it does actually give you a lot of good information. So in this case, this is land seismic. We're looking at 60 kilometres depth, right down to the crust mantle boundary, which is shown in green here, at about 40 kilometres depth here. So we're looking right throughout the crust. And if you remember back to what I was saying at the start, is that mineralisation, and whether you're looking at collision zones of subduction and continental, volcanic arcs, mountain ranges or whatever, you have to look deep. There are big events and big structures that you need to look for, such as these fault lines that go right down to the mantle. So underneath the green line here is mantle, and above it is crust. That creates the migration pathways that Megan was saying is so important. So this is an example of deep reflection seismic in Victoria. It was conducted over the Victorian goldfields, and this is the interpreted seismic section here. If I put the locations of the known goldfields on top, you have Stawell, Bendigo and various other St Arnaud goldfields. What the seismic survey showed was that all these systems were linked to a common source. So this area here was identified as the location of the metals And as I was saying, the metals come from deep within the Earth. And 42 kilometres here is where the crust mantle boundary is. So underneath here is mantle. And these are linked, or the metal source is linked by various faults that are leading right up to the surface. And that's the migration pathways that these metals took to get deposited near the surface of the Earth. What the study also showed was other faults that didn't have known gold fields on it, and this has opened up new areas where there's potential for gold mineralisation. So that was seismic. Moving on to gravity. You can measure the density distribution using gravimeters like this one here, and you can map out large areas doing regional studies and map out the whole state or a continent. And in this case we have New South Wales and Victoria, and what you see, red is basically high density material, blue is low density material, and so as I was saying, low density sediments. So this is the Darling Basin here. So you can map out where the basins are occurring. Over down near the bottom, Gippsland Basin, which has producing coal and oil and gas reserves. And I have to say that all this data is pre-competitive data, as Andrew was saying at this very start. It's distributed freely so that all the companies, anyone who wants to use it, can get access to it. And these types of very large area, regional scale studies are conducted by state governments, state territory governments, as well as federal. Magnetics, you can use instruments like these to collect the magnetic distribution of rocks under the ground. But that's, to cover a large area by ground is very difficult, so we can also mount it on aircraft, and you can see the stinger behind the aircraft here, which houses the magnetometer. And again, you can create regional maps of magnetic distribution, and these give you an idea of what the materials are under the ground and also how deep they are. If you look at all the spotty stuff, say up here, it's high frequency data. It's very, you can tell from that it's very shallow. Whereas over here, where the Darling Basin, where I was pointing out, it's very broad features. And so you can tell from the magnetics, by being broad and long wavelength, that it's very deep. The magnetic sources are very deep in that area. So now on to drilling. So drilling gives you the ultimate in information about the Earth at depth. It gives you samples that you can work with, and you can analyze it using, say, high logger, which looks at the reflectance of say, the core in this case, and gives you an idea about the composition of the material. However, drilling is very expensive, and you can only do it, and you only get information from one location. So you need to combine it with all the other data sets that we've got, such as magnetics and gravity, to get a broad understanding of the area. So this is an example drilling project, the Staveley drilling in Victoria. And going back to the theme of exploring undercover, most of what you see here in yellows and greens and the lighter colours are cover material. These black spots here where the volcanic arc, and remember what I was saying, volcanic arcs associated with mineralisation, that's the outcropping material in Victoria from that system. So where do you think the current prospects are in this area? Well, it's where the black spots are, and they coincide pretty much exactly. That's because they know that the material's there, they can pick it up, they've sampled it, analysed it, known that it's associated with mineralisation. That's where the prospects are. However, by doing this drilling project, and you see this, this is the magnetics backdrop to the study area. You see various bands of highly magnetic material, which we didn't know what they were before this study. And the black spots, the black dots, where we drilled into the basement material by rigs such as this. And from this study, what we found was that a lot of the magnetic material that was shown before was linked to mineralisation. Using geochemistry and geochronology, by dating the samples, we were able to find that all those various rocks were linked, and they were linked to mineralisation. So now, from the study, this brown, all this brown area here has been opened up for potential exploration. So that shows the workflow that we do. We use all these data sets, put it all together, conduct some drilling, and get preliminary information that we can open up new areas under cover, and then off to the exploration industry to take up tenements and further exploration in more detail. So moving on to energy, exploring undercover, although it's a minerals-focused area, it can also be extended to petroleum and oil as well. So this is an example from Queensland, where we did a seismic survey back in 2007, and we discovered a new sedimentary basin that was previously unknown. The green on top here is the Carpentaria Basin, and shown in orange is the new basin that was discovered by doing the seismic. And what it shows is that there's potential traps with the folding and the structures here. And if you look at the depth, well, it's not quite enough. It's about 3.2 kilometres. And to produce oil and gas and cook it sufficiently, getting the right conditions, the Goldilocks conditions that Megan was talking about, you need about 4 kilometres depth. So it's not quite deep enough over the seismic line, which is shown here over the gravity. But if you look further to the south on the gravity, it shows a low, which indicates a deeper sediment. So this area could host oil and gas resources. And back to the Bight Basin. So Australia, as it was moving north, opened up a sea, sediments were deposited, and that's where the Bight Sedimentary Basin is formed from. So that area has been very much underexplored. There's no producing oil in that area, but GA, through a number of years, did a lot of studies in the area to get pre-competitive data. They did some seismic survey and collected preliminary data over the area, and also did some dredging to collect samples. And they dredged along a canyon line so that they can get samples from various layers in these sedimentary sequences. And what that showed, or what they found, was source rocks that could produce, could be the source of oil and gas in that area. And that generated a lot of interest, and BP took up some exploration leases in the area a few years ago. Oil prices being the way they are, they've pulled out now, but that doesn't mean to say the area isn't prospective. So basically what I'm trying to say is that by doing preliminary data in an area, you can promote exploration activities. So if you were an investor and you had a prospectus, and in the booklet you had that, which is basically just a map of Australia in its outline, you probably won't be very interested. But if you had a surface geology map, which is a fantastic data set that we have here at GA, because this was collected over decades and decades by state and territory governments, and there were so many discrepancies at the borders, and we were able to produce a seamless national data set. So this makes sense. But it shows a lot of cover material, so you might get scared away by looking at that sort of geology. But then we have numerous other data sets that, like gravity, magnetics, radiometrics, seismic, geochem, that gives you a lot of detail and a lot of information about the subsurface. So on top of all that, by combining all this sort of data, you can produce mineral potential maps as well. And this is a nickel, copper, PGE, or platinum group elements potential map of the whole of the Australian continent. And basically the red is showing high prospectivity, the blue is showing low prospectivity. So by having information such as this, you'd probably be a lot more interested and more targeted to where you're going than if you had no information at all. So that is what we do at GA to promote exploration activities in Australia. And so that's what we have. Where do we go into the future? Well, we have Exploring for the Future program over the next 4 years. And we'll be focusing on Northern Australia, conducting a lot of regional surveys, which is shown in yellow for minerals, energy programs in green, and vast transects of airborne EM to collect conductivity data, MT, which is again looking at conductivity very deep within the Earth. And this will give us a whole lot more information that will guide exploration into the future and hopefully reproduce some of the success stories from the past. So in summary, mineral and petroleum resources are created from very large tectonic processes, colliding continents, subduction zones, and metals brought up from deep within the Earth. Mineral petroleum resources need a source, a migration path and trap to form a deposit. And there are many prospective areas that are hidden by cover, and we need to combine various data sets in order to explore effectively.